Then the next talk is given by Mónica Morales Masis from the University in Twente. Mónica started her life in Costa Rica and also her studies, and then also partly studied in the United States, after which she moved to Europe, worked at EPFL, did her PhD in Leiden, and then a postdoc in EPFL in Switzerland, and then moved on to the University of Twente, where she leads her own group and now is a professor. Her interest is in the growth of semiconductor layers, hybrid materials of all different kinds, organic, inorganic, hybrids, perovskites now also. And she's also worldwide known for all the innovations in pulsed laser deposition that she developed. So it's a very interesting combination, I find, on fundamental material science, and at the same time developing new instruments that are needed to do that science. And that's where pulsed laser deposition is really a unique tool that Mónica has developed over the years. And that will be the topic of the talk today.
Thank you.
Here's a clicker.
Thank you. Thank you, Albert, for the kind introduction. And yeah, it's a great honor for me to be here in this symposium that I had been participating in the past. And today I have the opportunity actually to talk about what we do in my group. Because we also have a panel discussion, I also thought about putting my own biography, but you already mentioned about what I have done. But then I can include something else. So we will discuss about career path. And I thought, yeah, actually I did study physics. So when I was in Costa Rica, I studied physics. It was very fundamental. And I did my PhD at Leiden University. But the way I got to work in PV is because I really had a very strong drive to work on material science. So what I did is I moved to EPFL, where there is a very strong material science department, but I actually ended up in Neuchâtel, where there is a very technological development of PV materials. So then actually I had a good combination of fundamentals and something very, very applied, where high efficiency devices are actually developed to really understand what is important technologically. And kind of that combination made me start my own group on really materials for PV, but really thinking about what is needed for example, upscaling, and what are the challenges that we have. So what I'm going to talk about a bit more is how actually we do these materials for PV. I also did some internships in Japan and US. I like traveling, and since I'm from Costa Rica, it was very easy to just move from place to place. And now I have my group, the Incube Lab. We work on optoelectronic thin film materials. We are in Twente, and we heard today a lot of people saying, oh, it's so far away. But it's just mentally. You just have to take a train, sit for 2 hours and work there, and it's fine to go to AMOLF or to go to other places. So we are in the east, very close to Germany, and this is the team. You probably already saw many of these faces here. They're all here. And I will talk about some of this work, mainly on halide perovskites, because we actually work on materials, and we have 3 main materials we work on. So it's basically transparent conducting oxides that Rolindo already mentioned. We work on P-type transparent material discovery and hybrid halide perovskites. And what we do is really a strong focus on synthesis of materials with a strong focus on physical vapor deposition, as you can see there. But once you make materials, you really want to understand these electrical and structural property relationships, because it's optoelectronic materials, it's electrical and optical property relationships. And once you develop these materials, you want to understand a little bit further, and then go to the other case where we can collaborate with people doing theory and really understand the material at the defect level and atomic scale, and optimize even further the material. But then you make materials, and then we also like to apply them, and we want to see, okay, did we make something, does it really work in a solar cell? So we need to make small devices and check if we can optimize it further based on the properties of the material. So that's how we go through the whole cycle. But I will not have time to talk about all the materials, so I'm going to focus on our work on hybrid halide perovskites. So I really had the advantage to be the last speaker, because we got a lot of introductions, mainly from Juliane earlier, about deposition techniques. So I hope I don't have to tell you why we actually care about metal halide perovskites. Basically, we are thinking about tandems, the future of PV, hopefully, and see how far we can go for high efficiency. So the field has been going already for a while, and what we have seen is that there are really many ways how to make these materials. Because they have very low formation energies, we can use all kind of solution-based methods. So in this paper, we summarize some of the methods that you heard already today, starting from the simple spin coating to hybrid methods, and also already for the solution process, we have really a scalability demonstrated, right, by using blade coating, slow die coating. There are even companies doing that. But there is a challenge because there is a lot of solution process, but when you think about solution process and you think about the halide perovskites, the compositions are very complex. So you need to use these salts, these precursors, and you need to find the right solvent to actually deposit that material. So you have kind of the limitation of solubility dependent, what I call solubility dependent. And that's why you need to go for like solvents like DMF that are toxic, and then you need to combine 3 solvents and so on. So it also doesn't become so sustainable, but of course, it's a matter of, I mean, we have to think about also the application. But that's basically the challenge of solution process. Now we go to the case of vapor phase deposition, where we have, I mean, we already heard about co-evaporation, and you saw from the presentation earlier that when you do co-evaporation, you have different boats for each of the precursor salts. And that's because each of these precursors for the perovskite has a different volatility. So what you do is you heat up, you use only thermal processes, and by heating up these ones independently, you can control the stoichiometry of the material. But once you have a very complex composition, you need a separate boat for each. Other process is something called flash evaporation. So what you do is you put all the powders and then you kind of explode them by putting a very high current, and they basically deposit. But it's still a thermal process, so it's very difficult to control the stoichiometry. And by looking at that, we went to, okay, let's look into pulse laser deposition to see if we can overcome this volatility dependence. And there is other, I mean, we are not the only ones, there is other techniques that are laser-based to also grow these halide perovskites. So, as I said, well, we have the motivation of perovskites, I mean, high efficiency solar cells and so on. But there are challenges, even though the field has been going for more than 15 years. It's about the control growth on the vapor phase. Basically, it is still a big challenge, and the question is, why do we want to do it compared to solution process? Well, one of the advantages is because it's solvent-free, so we want to get rid of the solvents. We also want to have the conformal growth, that, as you saw in the case of Juliane, that you wanted to do tandems, and then we want to make sure we can cover these pyramids. And finally, thickness control. So the proposition that we have when I started the group in Twente was, okay, we have these current methods, we can go for laser-based methods as a way to overcome the volatility dependence and the solubility dependence. So get rid of those 2 challenges by using, instead of thermal sources, a laser that basically is thermal and non-thermal processes that can ablate your material. So how do we do it? So this is a very nice animation from Tatiana that is sitting here, where we basically show that we take the precursors of the perovskites, so the people here doing perovskites can recognize the bottles. We take these powders, and we put it in the mechanochemical synthesis, let's say, vial. And just this with zirconia balls, we can just basically use mechanosynthesis that with mechanical forces, the perovskite starts to form, basically. So you can actually see in the animation how we have the precursor salts and how they become into the perovskite. And the important thing is we do this because we want to have a material that is very well mixed. When we have this material very well mixed, we can make it into a target, as shown here. And then we use the laser, quite controlled optics, actually, to ablate the target and then deposit our perovskite film from a single source. So because we can do this step, we can actually make targets with different compositions and then tune the composition of our films. And that's what basically how it works. We have a laser ablating the target. This is our substrate. And because we want to cover a little bit larger areas, we have the substrate that is actually scanning in the XY direction. This is a picture of the film, and this is how it will look in the same image. And by using this principle, the idea is if we want to go volatility dependence, then we can work with many different materials, from very standard cases, for example, cesium tin iodide, methylammonium lead iodide, and these combined cations like methylammonium formamidinium, but also because we are so independent of these materials, we can actually go for even material discovery, which means we go for things that are even more complex, like, for example, the case of chalco halides, perovskites that are also very interesting nowadays. So we started this around 2019, and this is what we have been demonstrating. And of course, some of the new work is based on wide bandgap perovskites for the future development of tandems. But I'm going to talk mainly about the methylammonium formamidinium lead iodide in this case. And what I want to show you a bit is like our developments. This is going to go much more in detail, but to maybe cover the different, let's say, stages of the audience, we do quite fundamental work when we go with very low deposition rates and try to get to epitaxial halide perovskites. We do something that is what I call medium deposition rates to do, for example, solar cell devices. And then we go for very high deposition rates to go to high TRL and actually make this a bit more interesting for industry in the future. So to start, I would like to start with the heteroepitaxy of hybrid halide perovskites. So the idea of epitaxy is to really get to the point where you can do a strain engineering of these materials and also single crystal halide perovskites. So we want to get to the ultimate case where you have a thin film that is epitaxial, and basically you have very little defects, and you can understand the fundamental properties of the material. So to do epitaxy, what you look at is what kind of substrates you can use that will have the same lattice match as your halide perovskite. So in this paper, we also summarize some of the substrates that you can use. For example, potassium chloride with a lattice of 6.3 angstroms match really, really well the cubic phase. Well, not very well, there's a little bit of a shift, but with the case of MAPI. So the idea is you have a cubic substrate, and then you put a cubic perovskite on top. And of course, that was a hypothesis, but then Junia came to start in the group. She's also here, and she had a poster, and she had that challenge to demonstrate that it was possible. So we use PLD. So we use a target of methylammonium lead iodide, and then she controlled the growth to actually show we can do this epitaxy. So this is a little bit of a summary. I will not go too much in detail, but this is how the single crystal of potassium chloride will look like after cleaving. So you can see atomic steps, and then you put the MAPI, and it looks like that. Now, it looks a little bit grainy, so you say, okay, is it really epitaxial or not? In X-ray diffraction, you see is single-oriented in the 001 orientation. But again, here we cannot say much about epitaxy, but to confirm, we do reciprocal space maps. And I mean, I will not have too much time to explain, but basically, a single point in this graph means it's a single crystal. This is the single crystal of the substrate. And then when Junia grows the MAPI on top, you see a little point just below. So it's showing that your MAPI layer, your perovskite layer, in this case is 70 nanometers, is actually also single crystalline. Well, let's say single oriented. So otherwise you will see a line or something else. So that was a very nice thing to see. But what we wanted to prove, okay, this is just out of plane orientation, and this is confirming the epitaxial stabilization. So it's showing it's growing directly on top of the substrate. And I think there was a lot of discussions about collaborations. So here I would like to highlight that we also wanted to see how this goes on the film. And one of the nice things is here in AMOLF, we collaborated with Nikolai Orlov and Erik Garnett, and we say, can we do EBSD on this sample to see if it's really single-oriented? And if you are used to seeing EBSD, you will be surprised about this. Or at least we were very surprised about this. We were like, okay, this is fake, right? You can make a red square, that's it. Because polycrystalline films, we had different colors. But it was really amazing that we actually can prove with EBSD that we have a single-oriented film. So we have grains, but they are all single-oriented. And this confirmed, basically, is complementary with the reciprocal space maps. So it's a very exciting result, also an example of how collaborations can work when you have complementary characterization. And based on that, we can actually do a lot more characterization. But because of time, I would like to move to the next topic. And if you want more details, Junia has a poster still for later. So that was one of the first topics. The other one is about how we go for making actually solar cells. So the other motivation, of course, is can we make devices with this? And this is the work of Tatiana Soto here, Susana, and also Viria, that was a postdoc in my group. And here we actually work with methylammonium formamidinium lead iodide, because we can work with MAPI, but mixing MA and FA, it was, first of all, one challenge more, because we want to prove we can do the two molecules, but also we can stabilize the cubic phase on polycrystalline films, which is something that was actually known. I think in terms of what to say here is that because we work with these organic materials, and they are very highly volatile, we actually include a lot of organics in the target. So the target is not stoichiometric, we just make an atmosphere of organic materials when we do the ablation. So I already showed you how we mark the target. So we basically take the precursor, mix them in a target, and use a laser. And in this case, we have different amounts of Fa. And we also already heard from Juliane that Fa is actually a very difficult material to evaporate. So that was also a very good test in our experiments. And what we show is that by tuning the amount of Fa in the target, we can also tune the amount of Fa in the thin films. And we can demonstrate this by the shift in the PL. So this is the photoluminescence emission. And of course, if you change the MA and Fa ratio, your band gap of the material changes. So that was one of the first demonstrations, just basically on photoluminescence and the band gap. But of course, you also want to know the composition. So that will be the next slide. This is just a top view of the scanning electron micrograph of the perovskite as deposited basically in the PLD. And it looks like columnar growth. So it's very similar to co-evaporation, how a co-evaporated film will look like. Structural properties, so we have basically the cubic phase, and we have very highly oriented films. This is how it will look in the lab. These are the optical properties, so a band gap around 1.58 electron volts, which is expected for this specific ratio of MA and FA, close to 50-50. And then we can also do XPS to estimate the cation ratio. So in here is the nitrogen core levels that are very different for MA and FA, so you can quantify or at least estimate how much you have on the surface. So now we could confirm that we have this, and based on the target that we use. But of course, XPS is a surface technique. So we needed basically NMR to see what is in the bulk and to confirm that we are not killing the Fa molecules because they degrade very easily, as we know for co-evaporation. So that's another example of a collaboration. We went to Radboud University, Professor Arno Kengens, and then we basically had to make very thick films, scratch them, and measure the NMR. But we managed to do that, and then you can see here is one example of the NMR spectra, where we confirm that we have a good ratio of Fa and MA. So we can say now, okay, we do this by PLD, because it was the first time we do MA-FA by PLD. I think nobody else did it before. This was a very critical measurement to confirm. We had the molecules there, the perovskite forms, and we can quantify the amount of Fa we had in the bulk. So it was a very important step. But then we needed to make devices. So we started with the NIP configuration, which I will explain a bit later. So this was one of the first solar cells. It was around 14%. And of course, the community is used to 25, 27, 30. So, okay, it was not that impressive. We have a bit of hysteresis. So, but still, for a new method, that was not done. And also, the PLD was just as deposited at room temperature, no passivation. It was already a very good first step. So the question is, how can we get to higher efficiencies? One of the things is you need to improve the fill factor. Olindo talked already about fill factor VOCs. We also needed to increase the VOC. So we know that in the field, everyone is actually working on passivation. If you look at all the record solar cell devices, there is always some kind of passivation in the bulk, in the surface, and so on. So we went for that approach. But before that, we also moved from NIP to PIN. So what is that? Basically is the polarity of the device, as we call it. So basically, this is where the sunlight goes, in this case and in this case. So you have, in one case, the first part is the N layer, so basically the electron transport layer. In the back is the Hall transport layer. And if you change the polarity, the first thing you see here is the Hall transport layer. We did not develop this, but we basically used the standard, let's say, device structure from many groups, which nowadays is a lot based on these self-assembled monolayers. So they are carbazole-based molecules that have a dipole moment that allows for the extraction of holes. So we basically took this as a substrate, so the ITO with the self-assembled monolayers, and then Tatiana went back to the lab to develop the same PLD recipe, but now in this type of devices. So the first question is, how does it look if you change the substrate? The substrate has a strong effect on the perovskite, but you can see we have a nice, dense formation of the perovskite films. So that was already good, and also a little bit of columnar growth. We also wanted to know how it grows. I know this is a very full slide, but maybe what we can look at is what happens when you have a very thin layer. So when we have a thin layer on the substrate, which is ITO2 packs, you have mainly lead iodide. We can see it actually very clearly there. So it seems that we ablate everything from the target, but only the inorganic attaches to the substrate first. So it seems to be something related with the sticking on the substrate. So here is lead iodide rich, but as you increase the thickness up to 400 nanometers, then the whole perovskite starts forming. So it seems to be kind of a two-step process, very, very similar to co-evaporation. So it's actually, we ablate the material in a different way, but the growth on the film is actually very similar. So above 400 nanometers, we have the full perovskite conversion. So now we understood a bit more how the material grows. And then we can actually say, okay, now we have the material. Can we go for passivation? Because the goal was to show if we can improve the solar cell efficiency. So one of the strategies to do passivation is to add lead chloride. This is something that is also reported in the literature, also for co-evaporation. So in our case, because we do in the target, we said, okay, now we add a fourth precursor in the target. We do the same steps, mechanosynthesis with some lead chloride at different amounts, 10%, 20, or 30% lead chloride. And what we see is if we add lead chloride, the structural properties are actually the same. So we keep the same orientation, not much shift. In XPS, it was not possible to see any of the chloride, so we still have kind of an open question on that. There are a lot of hypotheses, like lead chloride leaf or the chloride leaf, the sample. We still have to prove that. But you see in the PL, I mean, there was some shift, but we are still also discussing that because it's not correlated to the amount of lead chloride. It seems to be more stress in the film. But in any case, so we added lead chloride. Here we cannot say anything. We will see the results in the solar cell efficiency. Now, after the bulk passivation, we needed to do surface passivation. So for this, we actually collaborated with the group in KAUST, Stefan de Wolf, where they developed this very nice surface passivation based on OAMI molecules. So these are molecules just spin-coated on top of the surface of the perovskite, 3D perovskite, and forms a 2D perovskite layer on top. So now we have the perovskite and a 2D layer on top. And it actually works in our case. We prove we have the 2D perovskite. And by basically doing that, we make many devices. This is how the devices look like, based with the PLD perovskite, and then the passivation and the contacts. And by doing that, we basically went from the standard device that we used to have, 14%, up to basically 19%, above 19%. So basically what we learn here is passivation is really, really critical. We can make a film at room temperature, but we still have some defects that we could actually passivate nicely. And if you see here, I mean, there is basically no hysteresis. And the most important improvement is very clearly in the VOC of the device. So that was a very critical, demonstration, because now we can say PLD actually can produce films that can give a good solar cell efficiency, which is something that when you work on Halide perovskites is a question I was getting all the time. I was not planning to go so much in devices, but it was a critical step for the field to show we have to do it. And in terms of state of the art, so basically we look at just single source vapor deposition. Basically, this is the highest reported efficiency for getting very close to 19.7%, very close to 20, if you add this passivation. So it's a very, for us, it was a very exciting step. We are still waiting for a paper to be accepted, hopefully soon. Okay, and now I mentioned a little bit of passivation, bulk passivation. In that paper, we show everything on in terms of devices. But now we are taking a step further, and this is our next collaboration to highlight here, is with TU Delft, together with Jasmine Nespoli, that she's also here, and Tom Savenaya, because now we can also do mobility measurements together with them. And what we notice is very systematically that if we add chloride in our films, the mobility actually increases. And we do it with other materials and other deposition rates. And we can see in this graph that basically using time-resolved microwave conductivity measurements, that adding chloride is really helping to make probably the grain sizes larger and improve the mobility. And that's probably one of the reasons it is helping. So this is ongoing work, but also, again, an example of collaboration that we will benefit, also part of the solar lab. Okay, so for the last part of the talk, how do we go for high deposition rates? And why do we care about high deposition rates? Juliana already showed this paper. So in this paper, basically, it was really a question if vapor phase deposition is interesting for industry, if that will be the next step or not. And there were a lot of interviews with industry. And one of the, I will say, main messages here is that you really, if you want to do vapor deposition, we need to go for high deposition rates. If we look at co-evaporation, it could work, but it's still very slow compared to, for example, if you do sputtering deposition. And this graph, what it shows, this is the production cost, so dollars per watt. And you see that to get this down to here, which is the lowest possible, you need to increase the number of linear sources, either evaporation sources or laser sources, as whatever you want to call it. But also, you need to increase the deposition rate. So this is 120, this is 720. So really, to go for something that is industrially feasible or interesting, you really need to go for high deposition rates. So it's a very important thing to work on. There's some groups in co-evaporation working on that. And in our case, we said, okay, we really need to do it as well. So, and that's also one of the projects we have in the Solar Lab or Solar NL program. And so the way we are going to do it is like this. So we basically said, how do we do this, optimize it in a faster way instead of making films and devices, film and devices? So it was to actually install what we call in situ photoluminescence. So this is our vacuum chamber. And what we do in the vacuum chamber, we have a window at the bottom. So we can actually install the PL image, the PL, do it from the window at the bottom, as it's shown here. And then you look at your substrate during the deposition. So it's a good way to see what is happening if I change the deposition rate, and then you can screen very quickly if something bad is happening. And this is a project from one of our students, Wojtek Kliner. He's actually not here, but yeah, he did all the development. And it's also in collaboration with Martin Ledinsky. So I can just show maybe in the next one. So what is happening is we already know how the film is actually growing from the GVAX I showed before. But what we see here is basically in the x-axis is the thickness, in the y-axis is the peak intensity. And we notice that at the beginning of the growth, the PL is very strong, and then afterwards it actually goes down and it stabilizes. So, and also you see that the bandgap is actually changing at the beginning, and then it becomes very stable. So it's stable around 1.6 electron volt, which is the bandgap of the perovskite. This is what we learned from the standard deposition rate, but now we want to go for much faster deposition rates. So if we do the same measurement, at increased deposition rate, we see that the trend is exactly the same. I'm not going to go in detail, but the most important thing we learn at the moment is that if we increase the deposition rate to do a film of 500 nanometers in around 5 minutes, the process of PL and the growth is actually almost the same. So that gives us a good insight to say, okay, we should really optimize it to go for very fast deposition. But that's work in progress. So with this, I can go to the end of my presentation. So I hope I show you that pulse laser deposition is a good single source vapor deposition technique. It is solvent-free, so we are already in the dry process. It allows for conformal deposition. This is just an example of how we can deposit on crystalline silicon texture wafers. But also, what is very important is, there is, of course, the question, is PLD something that you can transfer to industry? It is still a question, but we are learning really a lot of how to make these very good targets and how PVD processes work with halide perovskites. So from there, we can actually design new PVD processes or think about strategies how to make it cheaper. So it's also important to look from the fundamental side of it. I show you that we can make devices with compatible efficiencies or competitive efficiencies. And now we are moving towards in situ monitoring and high deposition rates to also make this for possible industrial uptake. And with this, I thank you for your attention, all our collaborators and funding, and of course, the team that is very important that did all the work here.
Super, thank you. Okay, who has questions? Yes, Alex again.
Thank you, Monica, for the wonderful talk, and congratulations to these nice results, also to your students that you brought. It's nice that you came back at the end to the deposition rates, because I was wondering, First of all, when you vary the deposition rate, what do you actually vary? Is it the frequency? Is it the intensity? Is it the pulse
Good
length?
point.
And
Good point,
what is the limiting factor that influences your growth from increasing the deposition rate? The diffusion, the concentration in the chamber? I'm really curious.
Yeah, so I forgot to mention that indeed. When we increase the deposition rate, we basically change the frequency of the laser. So for epitaxy, we use 1 hertz, and then for the cells, it's 4 hertz, and here we went up to 40 hertz. And there are lasers that can go to 100 hertz. We don't have that laser, but yeah, it is possible. So that's, to increase the deposition rate, is just the laser frequency, because it's basically the amount of material you are ejecting from the target every time. So if it's 1 hertz, it's like you do once, it deposits, then you wait, and then you go for the next one. And if it's very fast, it's just you're depositing very quickly. So what limits? I mean, I think in terms of material quality, it will be the nucleation and growth. So basically, you have a lot of nuclei, and then if you do it too fast, at some point it will be too small. The grain will be too small. So you might need to play with temperature and other things. So temperature is also a challenge, because if you have temperature and your molecules arrive, they will actually go away. So you might have also that process happening. So that's why we do mainly room temperature deposition.
Okay. Who is next?
Thank you for the nice talk. I'm wondering about the reproducibility when you use the single target, because the major problems from the single target PVD, the target composition is broken by the repetitive deposition. So can you
yeah, that's
comment about that?
Very good point. We always get that question. I think I can look at my students now. But yeah, so basically the advantage of the way we do it with the laser is that you ablate really the surface. So it's a very localized thing. If you use a high, let's say, if you use a different laser that absorbs much more, you probably decompose much more the target. So because it's so superficial, like it's very, very small amount of material, you only change very small part of the target. And per deposition, there is a grinding of the target. So you like clean it, and then you go again. So you can use the target many times, but you do grinding to make sure that you don't use the old part.
Thank you.
Yeah, so I also used physical vapor deposition at some point, and I remember that the whole chamber was covered with perovskite as well as the substrate, so probably only 5% of the material ended up at the substrate, which is, if you think about industry and uses efficiency of materials, can be a problem, right? So I was wondering if this is different with PLD, can you really also target it to end up on the substrate, or do you also cover the entire chamber with perovskite?
Yeah, so that's also different because it's a little bit more confined. At least the inorganic part is much more confined. The organics, they do extend a bit more in the chamber. But we are still trying to demonstrate that. So this, our hypothesis is, for sure, it's not covering everything. I mean, you have to do many, many depositions. So in this way, it's different because evaporation is a big cone like this, right? In our case, it's like this. And that's why we actually really need to scan the substrate to cover everything, because you don't cover a very area just with one steady position.
So is this something you could control to efficiently transfer everything to the substrate, you think?
Yeah, so the way we control here is with the laser fluence, basically. So we need to also decide what kind of fluence we use and also the spot size. That's also another thing we have to, because the spot size is like how much the laser is ablating from the target.
Peter.
Yeah, thank you for a wonderful talk. It was fascinating to see how single-oriented your crystal columnar grains are. I'm still wondering, you know, there are crystal columns. I'm wondering whether you further want to optimize it, or do you know what the effect of these columns is on the transport properties, or are they effective or not?
Yes, yes, they are. I think I will have to go back a lot. But yeah, so we are working on it. Jonia is working on that, right? Yeah, so our goal is to have a single crystal. That's absolutely the case. I mean, I think I can go back a lot. Because you see, the small grain is the nuclei. There's a nuclei, but they are all oriented in the same way. But if you continue growing, it will be, as you said, columnar. So we did actually mobility measurements as well. And we see that it is limited by the grain size. So if you go to, if we manage to, like, how do you say, these grains do not have these grain boundaries and coalesce into a single crystal, yeah, that will be great.
Any influence on the substrate temperature while you deposit?
Yeah, so that's the problem with Ma lead iodide, so MAPI, you have the Ma that will leave the sample with temperature. But we think the substrate will actually play a role. So, I mean, that could also play a role. So we are looking into other substrates as well, but also other deposition parameters, because it can be still optimized a little bit more. You need a little bit more diffusion on the surface to get everything to coalesce. So hopefully we get there. we are trying.
Okay, I think this is maybe a good moment to stop, and let's thank Monica again for a fascinating talk.
Thank you.